Perfect, thank you. So yeah, welcome everyone back after the summer recess to the ICCS German Club. I'm delighted to introduce for this week, talking to is Milan Curcic, who's going to be talking to us. He's a scientist at the University of Miami's Rosenthal School, and with a focus on kind of ocean waves and their role in the Earth system prediction. But I suspect if you've come across him, it may have been under one of several hats. So there's the scientific work, but on top of that, there's also various sort of open source software contributions. And he's also sort of one of the key people involved with the Fortran Lang organization, and an author of the textbook, Modern Fortran, which he may or may not mention during the talk. So we met at PASS, where we sort of discussed several things that felt of interest to ICCS and sort of Vesri as a wider group, Fortran, machine learning, Earth system modeling, etc. And so that's why I invited him here to talk to us today about pure Fortran machine learning, why and how.
Thanks a lot, Jack. And thanks for the invite. And thank you, Paula, for facilitating, and everyone who showed up and expressed interest in this topic. I think Jack introduced well these basic details, but I'm going to give you some more background context. So I'm tenure-track faculty of ocean science at the University of Miami. I just started earlier this year. And basically, most of my research focuses on ocean waves, how they grow, how they break in general conditions, but I also have a focus on strong wind conditions, such as hurricanes and extratropical storms, and basically across scales, not just on the individual wave level and their physics, but also how the wave system affects the atmosphere and ocean circulation on the Earth system scale. And I do that with a mix of theory. I take field and lab measurements, and I also do some numerical modeling. Most numerical modeling is most in the context of spectral wave model development and coupling of waves with weather and ocean circulation models. I also wrote a popular Fortran book for beginners, and it's very hands-on, goes through practical examples, and does not teach the full language, but it is really meant for people who are already experienced with some programming and would like to learn more about how to use Fortran for their work. I'm not myself an ML practitioner yet. I probably will be at some point. I do have an ongoing project that is very AI focused, not necessarily Fortran related in any way. But I somehow, my life and career and extracurricular activities brought me to this point where I'm speaking about basically ML tooling in the context of programming languages and their ecosystems. And I generally enjoy making useful tools, software specifically for others. I mentioned my book here. I just want to tell you a little bit more details. I mentioned that it's practical, hands-on. It does have one running example. Running example means that there's one large application that you're building throughout the chapters of the book, and it's a parallel nonlinear shallow water equation solver. It's published in 2020. So far, almost 4,000 copies sold, which is not a big number in terms of technical book. Like it's a really small number of sales compared to, say, the hottest JavaScript frameworks. But my editor promised that this book will sell a little bit, but for a long, long time, just because of how mature the technology is. And indeed, that's happening. Basically, the sales have plateaued at some level and just keep going. It's pretty highly rated on Amazon, but why I bring this so much, not so much as a sales pitch for the book, but also because it's a hook in the story, how I got into making a machine learning framework in Fortran. It was basically I started learning that stuff when writing chapter 6, an early draft. It didn't make it into the book, but it did leave me with this open source software that I continue to build. So my title is Pure Fortran ML, and what does that mean? So Fortran, probably don't need to explain to you. Many applications remain written in Fortran for historical, cultural, and/or practical reasons. Some new projects are still being started and developed in Fortran. Really depends on, who's on your team. Do you have existing Fortran expertise, and do you not have technical requirements for which Fortran is not the best fit? And we'll discuss that a little bit later. Machine learning or ML, a very useful tool for classification and prediction if you have a lot of data. But state-of-the-art ML frameworks are written in Python, typically C++ backends. And when combining with existing Fortran applications, it introduces an integration complexity. So we'll talk a lot more about that a bit later. And then pure Fortran ML. Pure Fortran simply means no external dependencies, no dependence on other languages. Typically, just a Fortran compiler is what you would need. And Fortran itself provides all the necessary building blocks for ML, making it this approach at least a candidate to applying ML and physics-based Fortran models. And really the challenge with Fortran is really not so much about the language, but really about the lacking ecosystem that has, over the past few decades has not been nurtured or developed as much as for more recent languages that came around about when internet started. And I just want to give you just a short taste of what my, more or less typical research day looks like. So I'm part of a bigger experimental lab that studies ocean waves. We put sensors in it. We run various wind and wave conditions. So I'm interested a lot in the wave impacts on air sea fluxes. And this is just an example of the kind of data that you would get from these experiments. So basically, it may be a shotgun of scatter plot of data against some independent variable. In this case, this is the air sea drag coefficient. It's a function of wind speed, and we parameterize this. So you would, let's say, in a simplistic case, you would fit a curve to the scatter, and you would implement that in a full circulation model. So that's the connection, how experimental data gets into research grade and production grade numerical models for prediction and research. And this is the animation of output of a global atmospheric model. Specifically, this is MPAS, model for prediction across scales. I borrowed this animation from my colleague Falco Yute, who ran the simulation, mainly because it just looks really pretty and kind of resembles things that you would see from a geostationary satellite. And here I want to illustrate just the vast range of scales that you get as emerging patterns from solving partial differential equations on a grid or an unstructured mesh. And none of these patterns like fronts and cyclones that you see, these are all, I said, emerging patterns, and which means that they're not encoded in the equations themselves or in the code. And that's just fascinating that, we code things on a grid level, on a grid cell level, and these beautiful realistic things that just come out. And this property also enables accurate prediction to an extent. Of course, the curse of it is that the equations are nonlinear or chaotic, so small errors in initial conditions grow, and that effectively puts a predictability limit. And this occurs in weather, ocean, alike. So I mentioned nonlinearity already, but I want to point out that Earth system is complex. It has many different interacting components: atmosphere, ocean, waves, land, sea ice, and so on. And these cross many spatial and temporal scales, and they also have nonlinear feedbacks between them. So if you run just an atmosphere model, you get one solution. If you run atmosphere model and an ocean model, and you let the information from the ocean propagate into the atmosphere, you get a different solution for the atmosphere, and likewise for the ocean. Predicting the Earth system is crucial for most of us in our daily lives. We all know this, but yeah, I just want to show you the slide. So as a reminder of what motivates us to do this work, both weather forecasts and climate projections are essential for human well-being and existence. Under the hood, these models I mentioned, they may be discretized on a grid or on an unstructured mesh, and we solve partial differential equations. On the grid, in the vertical, it can be discretized in various ways, but basically you have these pancake-like layers that are stacked one on top of another. And basically, the physics that occur in the horizontal versus the vertical in both atmosphere and ocean are pretty well separated, thanks to just different fluid mechanical properties of rotation and stratification that makes it essentially a two-dimensional flow, and you need to do some special things in the vertical to correctly do the mixing and transport of properties. So now down to the practical level in the code. What's in a typical weather model code base? Or let me take that back. Maybe not typical, but let's take a very popular open source model used both in research and prediction. And this is the one that in the past I have worked with the most. So that's WRF weather research and forecasting model. It has about 1 million lines of code, mostly Fortran, some C. It has domain code, so subgrid scale physics parameterizations. When you dig through the code, you see layers that really quite clearly originate from different decades over the past half century. And that's also come in a variety of Fortran dialects. Also depends on linear algebra and fast Fourier transforms. So typically it just pulls in some of that linear algebra coded directly into the WRF code base rather than pulling an external library as a dependency. And that was just a practical and easy thing to do. And HDF5, NetCDF, and MPI are linked in as external dependency, and optionally you can use OpenMP directives for multi-core processing. And my main takeaway here is that it's a very complex code base that scales well on CPUs, but because of this complexity, it has not kept up well with emerging hardware accelerators, so specifically GPUs. And that has been one main technical reason why we see many large climate, weather, ocean projects migrate some to C++. There are some Python frameworks that do that, like source translation stuff. There's a big climate and ocean project in Julia. So we see a lot of models being rewritten to C++, Python, or Julia. But a lot of models implemented in Fortran remain to be continue to be maintained and developed as is. So one key technical question here is how then to run weather models on GPUs if source code wise they were not properly designed and planned for such hardware. You can use directives to offload, such as CUDA Fortran, OpenMP, OpenACC, HIP, typically depending on the kind of GPU that you have, whether AMD or NVIDIA, more recently Intel, you would just use different technology to offload, and that's really, really tedious and cumbersome, because if you want to support more than one GPU, you effectively need to do very complicated things about the code or maintain two versions. There are also source-to-source translators that are emerging. I mentioned rewriting to another language. These are typically very big projects. From my experience working with various teams that develop models, building a large climate, weather, or ocean model from scratch is typically a 100-person year project from 0 to production grade. So that means 10 people could be working on it for 10 years. That's something that we see with Department of Energy projects, like and same with the climate project, which is the Julia-based project that has now been going on for almost 10 years. And alternatively, you can develop machine learning emulators for all this kind of messy subgrid scale physics code that's that's written in a code that it's very difficult to maintain and understand. And so you can build emulators for it. And the kind of not so often spoken about advantage of this approach is that if you emulate a piece of a subgrid scale physics code with essentially a large matmul, that will also be very easily offloadable to a GPU. So you kind of you get 2 for 1 there if you succeed. So I'll talk a little bit more about machine learning for Earth system modeling just to set the stage for my main interest here. And I like to use these. I kind of made a meme out of it, but there are these quotes which I'm sure you've all heard before. Mark Andreessen said, "In early 2010, software is eating the world." And Jensen Huang, lead of NVIDIA, said in an interview in 2017, "But AI is going to eat software." And I love that because it is truly what we've been seeing in the past few years, at least in the Earth system and numerical weather prediction field. And we have indeed, with AI-based modeling, we've entered a new era of NWP. AI NWP models do prove to be orders of magnitude faster than physics-based models, and they do now match or beat the accuracy on some metrics. You see releases from various models, and it's always kind of a race. Oh, we beat the physics-based IFS, and then another AI model comes out, we beat this AI model, and there's certain metrics that are used there to quantify the performance. And I don't mean to say that they're carefully selected to bias the to bias the model positively. There's an established set of metrics that everybody agrees to use. So it's a fair game. But what I want to say is that in a general sense, and especially if you consider research, you can pick any model and you can poke holes at it and find reasons why it sucks. And of course, there are reasons why it's awesome. But none so far are an end all. Really, the main progress has been in really fast and really good prediction. But if you need to customize things, if you need higher resolution, if you need, let's say, very detailed tendency outputs that were not present in the training data set, data emulators simply won't help for that. And they were not designed for that. But I do want to point out that these models do appear rapidly, and almost on a weekly or monthly basis, we see big news releases about AI models, and they're extremely useful for prediction, but they're not yet replacing the physics-based models, at least in the research space, because ultimately, database models need data to be trained on. Typically, that's, say, ERA5. But ultimately, you need a physics-based model to create ERA5. And ERA5 does have some built-in biases that come from the subgrid scale physics of the model used to generate it. Despite, of course, all the observational data that's assimilated in it. But I think really there's always going to be this complementary role of AI-based approaches and physics-based approaches in both research and prediction, at least until we have really instant, accurate, full Earth coverage of observations, which we all know is very, very difficult and far in the future. So I mentioned the traditional and ML-based NWP. What's the difference really in traditional models? I like to say to people that ask me, basically we ask how to model the physical process that takes state X at time t to the next step in time. In ML-based models, we ask, really dumbed down in a practical sense, what weights in a matmul best map state of X at time t to the state of X at time t plus delta t. And this is the pure data emulator approach. There are, of course, in AI-based models, there are a lot of hybrid approaches where, for example, you can have your dynamical core to be auto-differentiable. And then with the help of data, your model is learning the subgrid scale tendencies that help this explicit dynamical core match the data. That's what, for example, the neural GCM from Google does. But the key idea in this data-based prediction is that any process or data mapping can be modeled with a matmul, and that's also convenient because a matmul is also very easy to accelerate. Again, thanks to the recent explosive developments in both GPU technologies and AI methods. So in the context of existing Fortran applications, basically we have a two-language problem, which is the original Julia pitch that it addressed, is that basically virtually all our system model components are written in Fortran. And here I just list out a bunch for you. I'm not going to talk about them, but just to point out that there are so many. And all of these are used in some research or operational capacity in the world for mission critical stuff. So this is not like, oh, we have 10 flavors of one thing and, you know, mainly one is used. Really, all of these are used for different applications and scenarios. Meanwhile, mainstream ML are basically Python frameworks. And here I consider PyTorch, TensorFlow, and JAX as the main popular ones, let's say. So the poor domain scientists ask, and by poor domain scientists, I mean somebody like me, how do I run ML within my Fortran application? And there are multiple approaches. A really simplistic one, you can just have a two-language disk-based interoperability, and that's what Fortran Keras Bridge did. That was a 2020 project that forked off, that used a fork of neural-fortran as its Fortran backend. But basically, what you're doing is you're doing some training in Python. You save the model to a file on disk. Meanwhile, you also have a Fortran application running that's reading that reads that file and then does its own inference that is coded by hand. You can also use bindings through Fortran C to Python interoperability. There's a few for PyTorch. I'm aware of one for TensorFlow. I know Jack and probably a few others here have been involved in a few of these. And there's also an alternative pure Fortran ML approach. I mentioned that Fortran is a natural fit for ML. It has first-class multidimensional array support, so like NumPy. It has matmul.product, sumpack, unpack, reshape. All these kind of essential building blocks are part of the language itself. And Fortran's philosophy for a long time has been that any hardware specifics or how to do things, how an algorithm should be implemented in terms of the order of operations and things like that, that is not Fortran. Fortran as a language, that's not its business. That's compiler's responsibility. So in the language, you simply express your algorithms through language elements, and you let the compiler generate the best code it can. Now, unfortunately, that part of Fortran's struggles over the decades has been, over the past, let's say, 2 decades, is that compilers, because of decreasing use of Fortran in the world relative to other emerging languages, the compilers have also not kept up in supporting the emerging hardware as well. But it also has fast linear algebra libraries, no complexity associated with multi-language applications. So it simplifies development and integration and deployment. And also we need to remember the human or social aspect of this, is that many Fortran programmers would love to use Fortran for their ML work. So this is where I'll talk more about neural-fortran specifically, which is the deep learning framework for Fortran that I created several years back. So I mentioned that was during the writing of my book in 2018. I was writing a chapter about teaching derived types, and I thought, oh, these neural nets are becoming popular. I know nothing about them, but it seems like derived types could be a good sort of data structure to model the layers of arbitrary sizes and all that. So I thought, oh, why don't I use a neural net as a practical example for the chapter? It ended up being a monster chapter of 80 pages, and the editor was very upset because she said, you're teaching both derived types and neural networks in one chapter. Please get rid of neural nets. So I ended up with this basically code that I just put on GitHub, and maybe it'll be useful to someone. I wasn't doing any ML work at that point yet, but once I put it on GitHub, I started getting emails, first once, twice a week, then sometimes every day, mainly from people initially from China and India, basically thanking me for the project and asking to implement some more features. But then more people from Europe and US started writing. So I know that people noticed it. Some people were using it, but I kind of, for me, that was a hobby project that was done. I could just kind of let it go. And actually, I realized that I'm telling you the origin story, which is this slide. And then about 6 months later, an editor of ACM Fortran Forum, which is a now defunct online journal, that basically published papers specifically on Fortran and Fortran applications, invited me to write there. I wrote a paper that got it a little bit more noticed. Actually, that paper is now like more cited and more used in other work than most of my other scientific work, which is funny because they put so much time into the domain science. And in 2020, Jordan Ott, who was a PhD student of Mike Pritchard's, who is now at NVIDIA, so he thought this was a good, neural-fortran was a good case to use as a Fortran backend and to make this Fortran Keras bridge. And that's the disk-based interop approach that I mentioned. Nowadays, Fortran Keras bridge is mostly of historical significance. It still relies on TensorFlow and Keras version 1. So it's mostly, I'd say, deprecated. And then I got a small NASA contract to redesign and add more general layer types as they were integrating neural-fortran in their global model. So that basically, all these signals from various sides that, okay, people want to use it. People started publishing papers about accelerating their physics code with it. So there are all these little success stories that, I just started hearing about. So I thought, okay, maybe it would be useful to push this a little bit more and see if it can be useful to many more people. So design principles are basically, my number one is it must be easy to use. It must have a nice, concise, high-level API, kind of akin to I modeled it after Keras's sequential model API, if you're familiar with that. Basically, you stack the layers in a network constructor, but I'm going to show you those details in a bit. Easy to extend, so we can easily add other types of layers, optimizers, other algorithms. It must be hardware agnostic. At least that's what made it easier for me. Still, for now, I want to let the compiler optimize and accelerate for, let's say, for GPUs. And compilers are coming more up to speed with that. Now there are at least a few compilers, Intel, NVIDIA, Fortran, and I believe AMD Flang that can take your do concurrent loop and offload it under the hood without you writing anything special about it to their GPU. And also self-contained, meaning as few external dependencies as possible, really simplifies for people to just pick it up, build it, and run it and play with it. This is a minimal training example. I just want to show you what the code looks like. I have lost my pointer. Okay, here it is. So this is where I construct a network. In this minimal case, I really just say, okay, I'm going to have an input of 3 neurons. I'm going to have a hidden layer with 5 neurons. And I'm going to end it with the output of 2. And super minimal, I'm just going to give it constants, and I'm going to expect constants in the end. So really just arbitrary numbers. I have a sequence of digits here and a sequence of digits here. And basically, the network just, through backprop, in this case with stochastic gradient descent, it optimizes toward that solution. I think I can show you here real quick. I'm in the root directory of neural-fortran, and I'm going to quickly build it and test it with FPM. FPM is the Fortran package manager. And I'm going to run this example that was showing you, which I believe is called just simple. And it ran, and here I'm just showing you the output where in each iteration it optimizes toward these values. Of course, this is a minimal toy problem. You won't do this in practice. You want to loop this through a lot of varying data, and your network should converge toward a state in which it can map arbitrary inputs that's in the range of your training data and give you some useful prediction. Maybe some more, a case that's more reasonable for a practical use, which is a convolutional network for, in this case, this is business for the MNIST digit recognition, which is also toy data set that is often used to test and do demos of networks. But here I want to show you is that, yeah, you open this network constructor, and you just stack. These are constructors for the layers. We have an input, a reshape layer, which transforms the sequential one, the input, into a 3D array. Then we have a convolutional layer, a max pooling layer, another convolutional and max pooling, and then we end with a dense. And then we have what you have, say, in Keras as a compile and fit. Here is just one step where you do net train, specify your input and output data, batch size, epochs, number of epochs, optimizer, and so on. I also have this. This was the part that's among a few other things funded by NASA, which is an optional and separate plugin for neural-fortran, which allows you to load Keras models, say, in HDF5. And what's really cool about it is that you install this plugin with FPM, and your interface for the network doesn't change. You don't use any separate function. You still import network for neural-fortran, but instead you pass it a path to your HDF5 file where you have your saved model, and from there you're ready to run inference. And I have, in this repo, I have examples of doing that. Neural-fortran is competitive with at least Keras 3 with a TensorFlow backend, and this is a single core CPU performance. I'm not showing any. I actually haven't run a neural-fortran on GPUs yet, and this is for that related to the design principle, where I don't want to write any hardware-specific code in neural-fortran itself, because the hardware and software field is moving so fast that honestly, even going to the latest conferences on this, I have no idea like what's the best thing to use. Whether I should use OpenMP or OpenACC, or just let the compiler accelerate, do concurrent. So for now, I'm just letting compilers get up to speed with proper offloading to GPUs. And then we'll see how we get there. But I was actually, so I did this for this comparison specifically for this presentation. And last time I did it, actually these, so from left to right, we have two versions of neural-fortran with G-Fortran. Then we have Keras 3 with TensorFlow. Then we have neural-fortran with classic iFort, that's in the old Intel Fortran compiler, the new Intel Fortran compiler, and the LLVM flank. So they're sorted in ascending order. This is elapsed time, so less is better. But somehow, before a recent refactor, actually G-Fortran was on par with Intel Fortran. So it was, this example would come out at around 9 or 10 seconds for G-Fortran. But with a recent refactor, which is really about simplifying some loops in the forward propagation, G-Fortran now really flies with neural-fortran flies with G-Fortran. So it's about twice as fast as the equivalent example of Keras tree with TensorFlow. And these other compilers are lagging. But in general, what I want to point out, at least on the CPU single core, and neural-fortran implementation is really naive in how it does. I don't do any special tricks in how about the order of operations, the loop layout. Basically, I write the simplest modern Fortran code possible and let the compiler do the work. And it's still very competitive. I'd love to add the PyTorch example to this. I'm just not yet as familiar with PyTorch, but I'll add it to this list. I'm really curious how it shakes out. But I suspect that PyTorch is probably of similar performance on a single CPU core as TensorFlow. Go ahead, Miran. I see that Miran raised hand. You can ask a question now.
Of course.
Sorry, we were muted in here. Well, I was just going to ask, what effort did you make to kind of make the compiler flags between all these different compilers as consistent as you could?
Yeah, I just optimize as much as I can, which is the highest level optimization. I also allow the standard breaking floating point order of operations, basically. And I make sure in each of these cases, so this is training a dense network on MNIST, and I make in all of them, they converge to a target 96% convergence. So I know that they are, even with the reordering of operations, they do produce the correct result. But yes, here I'm really trying to push the compilers to the max. Keras and TensorFlow, I pulled that from PyPI with pip. I don't know how optimized it is, but I can see from the logs that it is using AVX2 at least instructions. And I do, for Keras and TensorFlow, I do force it to run on only one core. Otherwise, it goes a little bit multi-core. But just for a fairness of comparison, I force it to go single core. And hopefully in the, maybe in the next year, I will be able to run some of neural-fortran on an NVIDIA GPU with one of the compilers. Really, I mean, it's gonna have to be LLVM Flang. And I hope to make similar comparisons for training on GPUs. Okay, here I just give reference to some other Fortran ML libraries. You can click on them from the slide, but in the interest of time, let's just keep going. For neural-fortran and really pure Fortran ML to really work, Fortran really has to have a good ecosystem, good tooling, a vibrant community. Just language is not enough. That's why we have seen stagnation of Fortran over the past 20 or 30 years, is that the ecosystem has not kept up and the user base has shrunk. So just improving the language, which is a standard specification, is not enough. We need good compilers. And the language does keep evolving. The next edition will be 2028. It will bring powerful type-safe generics. So that's going to be a really big update to the Fortran as a language. And I know that the generics team on the standard committee are really putting a lot of effort into bringing the best features of type-safe generics from a few different languages. One of their models is how Rust does it with traits. But the ecosystem is growing rapidly thanks to the Fortran Lang open source organization, which started in 2019, rapidly grew to more than 100 contributors. Flagship projects are the standard library, the package manager. So package manager is what I used a little bit earlier to build and run the tests. It's really cool. It's designed after Rust's cargo. So if you've used Cargo, FPM should feel familiar. We have a modern website, a discourse forum for people to get help and to discuss. Also, new compilers are emerging. Fortran Lang actively collaborates with the L-Fortran compiler led by Andrei Chertik, now at Microsoft. And also we collaborate with the US Fortran Standards Committee. We participate in Google Summer of Code 4 years in a row now. Also get independent funding for various projects. And we're also now a non-focused, fiscally sponsored project. This is I want to show you just an uptick registered by the TOB ranking. TOB is it's not the most popular or the best ranking of programming language, and it's based on search engine indices. But I want to show you that there was this big slump in Fortran's quote unquote popularity for almost 2 decades. And at least following the start of Fortran Lang and the website and all the tooling that we've been building, there has been first a really big uptick followed by a dip, but hopefully a more steady increase that we will see over the next several years. I mentioned FPM. Let me see. Okay, so it's 12:50. We can stop and take questions, or if I can go 5 more minutes, I'm almost done. Is that okay?
Yeah, I think there's several people here who would like to hear about FPM, so it might waylay some of the questions.
Okay, great. Yeah, so here I'm just showing you the prompt of like running FPM. You can just grab a binary from the GitHub release page and learn how to use it and run it. It's really cool. It really saves a lot of work. It both integrates the dependencies that can be remote and the build. So it's both the package manager and a build system in one, very much like Cargo. I mentioned L-Fortran. What's really cool about L-Fortran is that it targets multiple backends. One of them is the WebAssembly backend. And here, because my slides are essentially HTML and JavaScript, here I'm actually running an application that is compiled by L-Fortran in the browser, and L-Fortran itself is running in my browser page on this slide right now. So I could change anything about this code and rerun it to change the image. Another really cool example related to ML of how you can run cool Fortran stuff in the browser is that here you can draw a digit and in real time get an in-browser recognition. Of course, this is just a toy example, but this is actually Fortran running in the browser. 3, 4, and so on. Okay. Oh, my slide froze. Let me see. Okay, here we go. Okay, here are my takeaways. I'll let you read it. Let's take questions. Thank you so much.